that if you put the charge in the box, any kind of box, cylindrical or anything, right, then the flux is Q enclosed over E0. And if we put it outside, right, and then we kind of saw why and how that works, then the flux is 0, right? So now let's see one of the main uses of how we use Gauss's law. And so one of the main uses of Gauss's law is to compute the electric field, or we could say derive, maybe is a better word, to derive the electric field of certain symmetrical charges. So we want to, the three main kinds of symmetries that we want to exploit, so is spherical symmetry, and we want to exploit cylindrical symmetry, and the other one we can call it, basically, maybe we can call straight line symmetry, for lack of a better term, straight line symmetry. So by using those symmetries and by exploiting Gauss's law, we are able to derive the electric field of certain charges using Gauss's law, easier than we would. So in other words, the Gauss's law enables us to calculate, to derive the E field, to get the E field easier than using this equation. dE is K dQ over R squared, right? This method. So in other words, the method that we did back in the previous chapter, where we found the electric fields of rods, rings, plates, right? That's kind of like this method, where you take pieces and you integrate them until you find the appropriate electric field of that shape. So we can maybe start with the straight line symmetry. So by straight line symmetry, this is kind of what we mean. We take a plate. So the plate can be a circular plate, it could be like a rectangular plate, right? Any kind of shape. When you're close to the plate, it doesn't matter the shape of the plate. As long as you're kind of close, the electrical field will come out straight from that. Kind of like your TV screen, your computer screen, right? The electrical field coming from it is straight for a while. And then when you get far away, then the electrical field starts bending. You see. So we want to be able to use Gauss's law to find the strength of the E field when I'm close to the plate. So we're going to say close to plates. So again, same thing with a circular plate. If you're close to the plate, we expect the E field to be straight. You see. So then what we're going to do is we're going to take advantage of this straight line symmetry. We're going to take a Gaussian surface like in this case, I would probably take a circular, like a cylindrical Gaussian surface like this. Right, so then I'm going to apply Gauss's law to that circular Gaussian surface. So this the electric field is coming out this way on the other side of the plate, straight. And then in this case, you can take a Gaussian surface kind of like this. A rectangular box. But at the end, it's gonna not really matter what kind of Gaussian surface we choose. But just to start, it's for the circular, it's nice to choose a circular cylindrical Gaussian surface, and then here like a rectangular box. So now I'm gonna say the total flux through there, EDA, is equal to the charge enclosed in there. So you're taking the charge enclosed within that Gaussian surface, you see. So since my Gaussian surface doesn't necessarily encompass the whole circle, it just encompasses that charge, you see, the charge within the plate. So then Q enclosed over E0. So this Q enclosed is that charge. Okay. Then apply the E dot dA. So since there is almost no curvature to the electrical field, the flux through the sides of the cylinder is 0. You see, it's kind of not like what I had here. Here, my box was kind of a long box. You see, so then the electrical field was coming out this way, and plus this was a point charge. You see. Whereas here, it's not a point charge, it's a plate. So if I'm close to it, there is no bending of the electrical field yet, you see. So that means I only expect the flux from this side and from the left side, you see. So what's the flux from the right side? E, and then dA is this way, right? So then it's going to be E times A, since E is uniform, EA. And then from the other side, you got E coming to the left, but the A is also to the left. You see? So it's not like you have a negative flux and a positive flux and they cancel each other. The electrical field is going this way, you know, left and right. You see, like this, like that. So if the E times the A, that's positive, this is also positive. So EA plus EA, that's equal to Q enclosed over E0. Okay, so then we can actually get the electrical field. It's going to be what? 2EA. So then E is going to be Q enclosed over 2A E0. And then that A is this area. In other words, that area is the area encompassed by the charge that's enclosed, right? So same thing in this case. In this case, it'd be the area, this area. So you're dividing that charge by that area, which means you're computing the surface charge density of that plate. How much charge is included in every unit area of that plate. So Q over A, we can substitute it with sigma. There you have it. So that is the equation for the electric field of plates. So we found the easy, quick equation for the electric field of any shaped plate. So now it really doesn't matter what the shape of the plate is. It could be a weird shape. As long as I'm close to the plate, the electrical field is like that, you know. So then I can say, okay, the electric field near that plate is just going to be the charge density, how much charge is included in the whole plate, divided by the area of that plate, you see? And then that's going to be the electrical field divided by the 2E0, you see? Any questions on that? I think that's one of the first equations that we used when I was first starting electricity this week. Remember the plate problem we did, the paper plate? Maybe you forgot already. I utilized that equation, sigma over 2E0. Electric field of plates. And of course, next week we'll also start capacitors, and capacitors are essentially two plates put together. You see, yeah, there you go. You see here? So in this case, they actually chose, you see, they actually have a square plate, but the Gaussian surface that they're choosing is a cylinder. It's not even a square. So really, it doesn't matter the shape of the Gaussian surface you choose in this case, since the flux is only through the top and through the bottom anyway. So you see, you're doing E times dA, and then E times dA, then you're getting E2A. That's equal to they kind of wrote it weird here. E2A is equal to Q over E0.
They put the A on top.
Oh, you know what they did? They wrote Q as sigma A. They wrote Q as sigma A. I would have just written here Q first, and then taken this to the bottom. Yeah, it's kind of confusing the way that they wrote it. It's better X this out and then write Q, and then take the 2A, bring it to the bottom, and then Q over A is the sigma. Because you look at this, where did the sigma first come from? You know, but the final result is the same thing, sigma over 2E0. You see. So if this is correct, we should be able to derive this with the previous technique. So if you remember, I still have the sheet a couple of days ago when I was doing, was it Wednesday maybe I was doing? Yeah, Wednesday. I was doing the electrical field of rings and plates, right? So remember when we got to the plate, this is kind of the setup of the plate. You say K, then you take a bunch of rings, then you say dE K dQ X over X squared plus R squared. Then dQ you say is 2 pi R dr sigma. Then you put it into here. Then the sigma came out, the 2 pi R came out, the X came out, everything. Then we integrated it from 0 to 0.5. But if I wanted to derive a general equation for the plate using this technique, I could find the general equation for the electrical field at any distance from that plate, you see. So if we wanted to, we could, let me rewrite that here. So with the previous technique, the electric field of a plate is what? K 2 pi R sigma X integral dr over X squared plus R squared to the 3/2 from 0 to R. That would be the general equation where R is the radius of a particular ring, right? R is the radius of the particular ring. X is the distance to any point we want to find the electrical field of.
Can I ask you a question?
Yeah.
Why do we have an extra R on the outside?
Oh, yeah, you're right. I can't take the r out. You got to keep the r inside. You have a 2 pi sigma k x. Yeah, I think that's it. So then we would integrate that.
You don't have a number. Which R are you going to use?
That's the thing, is I want to get a general answer now. Yeah, you see what I mean? I want to get a general answer so that I can compare that general answer to the answer we got from Gauss's law. You see? So it's, in other words, this is the ultimate test of Gauss's law. So we're going to do x divided by, in this case, x is the r. You know, x is the r. And then I'll put d squared plus x squared to the power is for 1.5, right? Yeah, 1.5. You see, so x, it's like you're doing x dx over d squared plus x squared. Maybe this website, we could put any variable, like I could even put r. Oh, no, because their default variable over which you integrate is x, I think. Does it allow you? Oh, no, you could change it. Oh, they even allow you to do that. Oh, I like that. So then we could actually make it the same variables. Or, oh, okay, so now it looks identical to our integral. Now it's r dr over r squared plus x squared to the 1.5. Then here I could have 0 to...
Professor, how did you do that? I was trying to get there.
Oh, yeah, you see here, this one? Variable integration, you can decide what variable you're integrating over.
Oh, you don't put dr into the calculator?
Into the calculator?
No, where it says calculate the integral of, and then you don't have to put the dr because it does it for you.
Oh no, that one I just clicked on it, and on the right it gave me, oh, what variable do you want to choose to integrate over up here to the right, and then you can choose over the variable that's you're integrating over. Does that answer your question, or?
Yep, thank you.
Yeah. Okay, so then it goes 0 to capital R. It's not going to do capital R. Capital R is the radius of the plate. No, it's not doing. Okay, that's fine. Let's see here. Okay, so this is capital R now. You see. Okay, so now.
What did you put for the limits?
0 to capital R, but it didn't have a capital. So we just use 0 to R, where R is the radius. This is the radius of every particular ring inside of the plate, and this is the big R is the radius of the plate. You see, but since it didn't recognize a capital, whatever this symbol is, it's just going to place it in there, and then that's going to be the capital R. So it's okay, you know. So this is now the capital R with the radius of the plate. So now I'm going to write that as 2 pi k sigma x 1 over x.
That's all right. I think I can't see the.
You can't see the screen?
Yeah, maybe it's my computer.
Do you see it? Anyone else see it?
I see it.
Oh, okay.
Okay, thank you.
Yeah. R squared plus x squared. Okay, so now Okay, so I wrote the integral result is this, and then x, there's an x outside, then I can distribute the x.
Did you put a negative? Oh no, that's not negative. No.
Yeah. I could distribute the x, and I have 2 pi k sigma 1 minus x over square root of r squared plus x squared. So this gives me the general electrical field of a plate, no matter how far away from the plate I am. So now we have because before this we had derived an equation for the general electric field of a ring. Let's see, where was that equation? Oh, this was. On Wednesday we did that. This is the general equation for a ring, kqx over x squared plus r squared to the 3 halves. So now we have the general equation for the ring, and now we have a general equation for the plate. We could do a couple things to this to see if the answer is making sense. One is take the limit as x goes to infinity, and what should the electric field of a plate look like as I'm going to very far away? Right?
You should start bending.
Yeah, it should start bending like a point charge. So its behavior should be like a point charge. So this result should reduce to kq over x squared when I'm very far away. Right? kq over x squared, where x is the distance. So two things should be true. For large distances, for large x values, right, this result should yield this. It should be a point charge. For small x values, then we could say it should give me this result from Gauss's law. So when I'm close to the plate, the electric field of the plate should be constant. Remember how we said the other day, the electric field of a plate doesn't come down and go back up? It kind of starts out like this. So then it goes up. Ring is completely different. The ring electric field comes down, it starts increasing linearly, right? So the strength of the electric field of a ring increases linearly for a ring. Let's see, because it's coming down and getting more concentrated. It increases linearly, then starts bending, reaches a max, then it goes like this, and then when you get far away, then it's 1 over x squared. But here it's proportional to x for a ring. For a plate, how should it look? And that's the other thing I can do, is simply just graph this and see what the behavior of that function looks like. I'm expecting this one to be constant for a while, the electrical field of a plate, constant, then starts dying down. And then as you get to infinity, then 1 over x squared. You see? So actually, we could, let me just plot this function. 2 pi k sigma. Let's go to Wolfram plotter. No. Oh, Desmos, yeah, Desmos. We haven't used that for a while. Desmos. Okay. 2 pi k sigma. Sigma, let me just use S for sigma. 2 pi k sigma 1 minus x divided by r squared plus x squared.
I think it's 1 over x minus 1.
1 over x. Oh, you did the limit thing?
Oh, yep.
Oh, okay. We'll come back to that too. Yeah. Let's see what's happening here. Close the parentheses. Close the parentheses. Power 1.5. Close the parentheses. Maybe we need to say y equals. Here's the graph. Too many variables. Try defining k sigma over r. Oh, I see. Oh, you know what? Maybe Desmos needs numbers, huh? Okay, let's just get rid of the k and the sigma. Let's just get rid of all that. And maybe put the radius as a number. 1. Okay. Oh, that's interesting. So the electric field actually dips and it's oh wait, no, it's not 1.5. Is it 1.5? Oh no, it's a radical. Something is wrong. The 1.5 before is for the integral. It's a 0.5, right? For the electrical field. Oh, that's a huge difference. Okay, there you go. So what is it saying? When I really zoom in, I mean, I have to really zoom in a lot. So imagine, in this case, the radius of the plate is 1 meter, right? So how close do I have to be to it for Gauss's law to work? Definitely not 2 meters. That's too far. So I've got to be really zoomed in. Let's see, zoom in, zoom in, zoom in. I mean, you got to really zoom in to be close. You know, very, very close, zoom in. See, this is supposed to be constant for a while, but it's not, because it's dropping. Let's see. So the equation sigma over 2E0 means if you're close to the plate, for a while the electrical field should be constant. But you see, this is not. Okay. Maybe if I really, really zoom in, you get the idea of that? You got to really zoom in. Okay, now you can kind of say, okay, the electric field, even then it's not constant, but it's not dropping by a lot when you're close. Okay, so the equation for that electric field is sigma over 2E0. Or the other thing I can do is make the plate big enough, right? So that even if I'm 1 meter away, it looks like I'm close. Do you see what I mean? So I can make the radius of the plate, let's make the radius of the plate 50 meters. That's a pretty big plate. You see? You see, now I can zoom out. Oh, now it's more obvious, right? Ah, there you go. You see? Zoom out, zoom out, zoom out, zoom out, zoom out, zoom out. Oh, for a plate that's 50 meters in radius, look, even if I'm 1 meter away, the electric field hasn't dropped at all. You see, it's sigma over 2E0, sigma over 2E0. Until about 3 meters away, then the electric field is dropping. Cool. You see that? graphical interpretations, that's where we're at here. You see that? So when I made the radius big, then you can kind of see that the electric field of a plate is constant for a while. Then when we go to the other end, zoom out, zoom out, zoom out, then when we go to the infinity, well, you can't really tell here, but you see this behavior should be a 1 over x squared behavior. So for example, if I go to 60 meters, what's the strength of the E field? 0.232, right? Or if I go to 50 meters, 0.294. If I go to 100 meters, what should it be? If it's already behaving like a square function, what should it be? You see, that's how we can quickly check is, has the 1 over distance squared kicked in? So we can just take a random distance and say, okay, it's 0.293 at 50 meters. It's 0.293. And then what is it at 100? 0.105. Is that as 1 over distance squared? Has the 1 over distance squared already kicked in? So what's the quick thing to do to check? If you double the distance and 1 over distance squared has kicked in, then the electrical field should drop by a factor of what? Right? Any function which is already behaving as a 1 over x squared, if you double this distance, what should happen to the y? No answer? If you double this, right? So then what happens to the y? It's not that hard. Come on, guys.
It's multiplied by a factor of 4.
Divided by a factor of 4. So multiplied by a factor of a quarter. So yeah, this should go down by a factor of 4. But I don't think it has kicked in yet. 0.293 divided by 4 is what? 0.07. So it's not decaying that quickly yet. This divided by 4 is 0.07, but the electric field is still maintaining. So that means the 1 over distance squared hasn't kicked in at 50 meters yet. You see, but if I go far enough, zoom out, zoom out. So now if I find the electrical field at 200, 0.03. Then go to 400, 0.008. So now take 0.03 divided by 4. 0.03 divided by 4. Okay, yeah, 0.0075. You see that? We're starting to approach the 1 over distance squared because 0.03 divided by 4 is 0.0075. And then I'm almost 0.0075. Okay. Okay, so then you can kind of see just from the graph here that it is beginning to appear as when we go too far away, it's 1 over distance squared. And when we are close, it's constant. Now, what was the equation for the ring? The electrical field of a ring. Y equals, from the other day, it was x over x squared plus r squared. Okay, it's x over x. We can kind of superimpose them I love graphing things like this, just seeing how it behaves and comparing them. Okay, so this is the electrical field of a ring, you see, and all other things being equal, I'm just putting X and then both of them with a radius of 50. So then how is the ring behaving? The ring should, let's go close to it. It starts at 0, right? Oh. Wow, it's so much weaker than the electrical field of the, let's see. It almost looks like it's flat, but it shouldn't be, huh? It should be, oh, it's so small. Oh, 0? It's always 0? Wait. X. Oh, it's kind of flat. That's weird. X over x squared plus r squared to the power of 1.5. It's weird that it's flat. Oh, because of the 50 maybe. So let's make the radius smaller here. Let's say 10 meter radius. Still small. Oh, now it's a little bit bigger. So for the plate, I could make it bigger and it's still got a very, oh, I see, because for a ring, the electrical field drops very quickly. So if I make it a radius of 10, you remember that we calculated when it reaches its maximum was r over root 2. So it immediately reaches its maximum, then it starts decaying. So the ring, the electric field diverges very quickly. So I gotta make it a small ring, let's say 1 meter ring. Oh, okay. Oh, reaches its max. Oh, there you go. Ha ha! You see that? A 1 meter ring. Now we can compare 1 meter plate to 1 meter ring. Let's see here. Oh. So this one starts here, but then there's some constants out in the front that I got rid of. So I don't think a ring will ever beat a plate. So those constants are important over here. So this is just graphing the behavior of them. So I wouldn't necessarily say, oh man, the plate actually is weaker than the ring, you know. So, but you can kind of see the behavior here. Here, the electrical field of the plate drops more. It's not constant because the plate is too small. So already within a half a meter, it's starting to drop. But you can kind of see the 1 over x squared behavior taking shape. Do you see that? 1 over x squared behavior. So whatever the field is here it should be 1/4 of that, kind of. Let's see. 0.29 divided by 4. 0.29 divided by 4. Okay, no, not quite yet, but it does look like a 1 over x squared. But the ring is going up linearly, right? Linearly, then curving, reaching a max. then dropping, and now the 1 over x squared behavior starting kind of like here. You see that? Okay, cool. So how do we do this now? The limit, in terms of the limit. We set the x really large number, right? But if we take the x large, how are we going to show that it has this behavior, kq over x squared? If we say x is large and we get rid of the r squared, right? So let me do this on another piece of paper. If I'm trying to find the limit as x goes to infinity, remember the technique that I was telling you, if this is a huge number, then ignore this one. But if I do it that way, I'm just going to get 1 over x, and then you're just going to be left with this, square root of x squared. So it's just 1 minus 1, and you're just going to get a 1. So that technique doesn't really work in this case to find the limit of that. When that technique doesn't work, we can employ a Taylor series expansion. We can write it this way: 1 over, write this one as, so factor out an x squared from here and write it this way. Write x.
What's that next to E, Professor? Is that a...
Which one?
The E equals...
Oh, that's E equals limit.
Oh, limit.
X goes to infinity. I'm trying to find the behavior of the electrical field. So I'm focusing on this part of it now, just to see. 1 minus, so now what I'm going to do is factor out the x squared from this expression, and then write this as 1 plus r squared over x squared. You see? So in other words, when I multiply that back in, it'll turn into an x squared in the radical, and then it'll cancel with this and this, right? So then this one will cancel this one. So this is the same thing as this expression. I just rewrote it. Then I'm going to rewrite this like this: 1 minus 1 plus r squared over x squared to the minus 1/2. So because this is a 1/2 power, so it goes up to the top, to the numerator, as a negative 1/2 power. So now if I want to exploit the behavior of this when this is very large, I can use this idea: 1 plus x to the nth power. The Taylor series expansion of that is like this. You see, so when you have something like this, an infinite Taylor series expansion of this, a power expansion, this can be always written like this: 1 plus nx plus n times n minus 1, 2 factorial times x squared plus nn minus 1, 3 factorial, and then it goes on forever. But if x is very small number, if x is much, much smaller than 1, if x is very small number, you can argue that you only need to keep the first 2 terms of this expansion. Or in some cases, keep the first 3 terms. But these ones keep getting smaller. Because if x is, let's say x is 0.01, small number. So then if you do 0.01 squared, you're going to get 0.001, you see. So when you add that to 0.01, it's going to not change this considerably, you see. But you could argue that, well, it's still big enough to maybe take value to it. But if you go 0.01 cubed, oh, that's so much more negligible, right? So oftentimes you can say, to approximate this, the behavior of this, you can keep the first two terms or the first three terms. So what I'll do is I'll keep the first two. Then if I get something meaningful, then that's it, I'm done. If I need to, then I employ the third factor. So why do I know that this is a small number? Well, because I'm trying to find the behavior of this function when x is large, when I'm very far away from the plate. So when x is very large, some number over a large squared, then that's going to be a very, very small number. So then I'll be able to employ this technique. So then when you expand this, you're going to do what? 1 minus, right? So take this and expand it to the first two terms. 1 plus, what's the n in our case? The n is this one, which is the negative half, right? Okay, and then times x, and in my case, my x is r squared over x squared. You see, so x could be basically whatever this thing is, that is the x. You see, so that's r squared. So I'm keeping the first term only, the x, and x happens to be this whole thing. You see, r squared over x squared. Close it and then end it there. So just go to the first two terms. I think that's going to be sufficient to get the result we want. So then what does this simplify to? So in other words, this function now reduces to this thing, and then the one that cancels the one, and then the negative distributes to this negative. So you essentially get half r squared over x squared. Oh yeah, look at what's going to happen. So now the electrical field is going to be what? When we're far away, when x is large. So then you get the 2 pi k sigma, and then half r squared over x squared. And then the 2 cancels the 2. Pi k, and then what's sigma? Sigma is the charge density of the plate, which is the charge over the area of the plate, right? And the area of a plate, since it's a circle, is pi r squared. Okay, so I'm replacing sigma by q over pi r squared, and then r squared over x squared. Oh my gosh, it worked out. So what do you get here? The pi cancels the pi. The
R squared
cancels the r squared. Kq over r x squared. Wow. So this whole complex equation has, we just proved that it has the behavior of the electric field of a point charge when you're far away. So that's the formal mathematical proof. So that means the plate equation makes sense from that point of view. Now I can take the limit of this as x goes to very small numbers. So now E for when x is small, x is very small. And then that's going to be 2 pi k sigma, 1 minus when x is small. then you ignore it and you just keep that, x over r. Oh, okay. It seems like the electrical field should drop linearly as a function of x. But if I'm very, very close, where x is so small, then it should be a constant for a while. Then as the x starts to grow slightly, it should drop linearly. Oh, you see that? That's what happens. Oh my gosh, this is, I'm getting my mouth is watery. This is so good. You see here how this is linear? But here it's not constant for a while because the radius is so small compared to the dimension of the graph here that it doesn't stay constant at all. But if I make the radius slightly bigger, okay, now it's kind of constant for a little bit and then starts dropping linearly. You see, that looks like a linear function. But it's not constant that long time. But if I make the radius, so as the radius grows, then it's constant for a longer time. You see, now it's kind of constant. Then it starts dropping linearly. You see, then as the radius grows to 50, okay, now it's constant for a longer time, till about 1 meter. So you see, on a 50-meter radius plate, 1 meter Gauss's law works very well. You see? So kind of think about it that way. Gauss's law works well on a 50-to-1 ratio. If a plate is 50 meters, you have to be within 1 meter of that plate for you to say the electrical field is constant. And same thing with your TV. Whatever the dimensions of your TV is, you have to be within 1/50th of that for you to say the light intensity is constant for that. So on like a 50-inch TV, right? So within something like within a 1 or 2 inch distance from the TV, the light intensity is constant. Then it drops linearly. You see? Then it drops linearly. But then when you're very far away from the TV, you know, then it starts to go 1 over x squared. You see? So this applies to anything that's like a computer screen, a TV screen, anything that's like a plate. Okay, so now we know that the linear is working from Desmos. Now, if we just make this disappear and we say take the constant portion for how long it's constant, 2 pi k, and now we want to show that this gives you the same result as the Gauss's law, which was what? Sigma over 2E0. So I want to rewrite that in this fashion. So then I use the fact that k is 1 over 4 pi E0. That's the relationship between the k and the 1 over 4 pi E0. So if I want to rewrite this like that, I'll just replace k by 1 over 4 pi E0. Aha, lo and behold, you get the pi, 2 and the 4, sigma over 2E0, man. Wow, there you have it. So now we proved roughly how long it's constant for, kind of a 1/50th ratio. We know that then after that it's linearly decreasing, but then when you go very far away, it's a 1 over x squared behavior. And we matched the result we got from Gauss's law. So this is kind of a test, one of the ultimate tests of Gauss's law, that when you do things in a general way and you find its limit, it should give you the quick result that you got from Gauss's law. So now let's go to cylindrical symmetry.